So, I am Malcolm Williamson. I'm going to be talking today about the my geospatial perspective of the built environment. I chose that name rather than just AEC because we work with some things that have been around longer than this domain anyway. I'm with the Center for Advanced Spatial Technologies, known as CAST, the research center at the University of Arkansas. And I want to talk a little bit about in the beginning, there were builders that built these great buildings here, but other than that, I wanted to talk just a little bit about my roots. So prior to doing what I do now, I used to be in industrial maintenance, and I used to work at Hiram Walker and Sons. They make liquor, and we had in Portsmouth, Arkansas, in the mid-'80s, they had one of the very first large-scale automated warehouses in the state. They had 40,000 pallets of booze that were stored, organized, and recalled completely without personal intervention. And I didn't realize at the time it was really pretty cutting edge there at that time. And in industrial maintenance, not only did we maintain things, but we also designed and let contracts on new things. So we were very interested in operations. And so that's really one of the things that's kind of directed my interest in AEC in the built environment, because I see kind of both sides of this picture. So these days I work at the Center for Advanced Spatial Technologies. This is a research center at the University of Arkansas. And so we are under the College of Arts and Sciences, but we're a department level entity. We report directly to the dean of the college, and more importantly is we collaborate with all sorts of folks. We have something that makes us rather, sets us apart from other centers like us around the country. First of all, we're not under a particular department. Secondly, we have around 15 full-time staff. Some of us have been there a long time. I've been there 21 years now as a full-time employee doing geospatial stuff. And so back in the early days when I started there, we were doing GIS and GPS. We worked with things like GRASS, which is still around as an open source GIS. And ArcInfo back in the, what we refer to as the dark info days, when it was all command line, and we had a set of books that was this wide with 900 different commands in it. We had pen plotters. This actually, the map on the right is one that we were mapping out land use around Civil War battlefields way back in, I guess like 92 was when I got started. And but even back then, in the days of 2D GIS, we were very interested in, we dealt with topology, the connectedness of things. And we also enjoyed the ability to have as many attributes about any kind of spatial entity we were mapping, recording. And we could ask questions about where things were and how they interacted with other things. And that really is a key point I want to come back to when we start talking about the built environment. One of the early problems that we used to face was how we would bring in, this is back in the day, 2D CAD data into GIS, because they didn't play very well together. You know, a lot of the CAD data, was a polygon, was really drawn up with line segments, didn't have attribution. How do we deal with that? There were some tools. In fact, there's a company, Safe Software, that started out back in that day strictly to deal with that problem, help you get CAD data into GIS and the reverse. And so even back then, we kind of dreamed about a truly global 3D GIS where we could map anything, we could record anything that was anywhere in the world at any level of detail that we wanted. And we could see the day that when computers were powerful enough and we could afford them, that we could do that. And I think we're getting there today. And I also wanted to point out that even back then, this is in mid-90s, I was actually 99, I guess. I was using the very first 3D scanner that I knew of on the campus. We were scanning models of primate teeth. And what were we using to analyze it? We were using GIS software because we realized it wasn't a geographic problem, but it was a spatial problem. And instead of inventing our own software, we just said, just change the scale, change the coordinate system, it works. Cool. And so that's what we did. That's what it really first hit me. We don't care about things being geo or not. And so back in 2003, 2003, we actually received a grant, a major research instrumentation grant from the National Science Foundation, which got us our first couple of 3D laser scanners. And because we had a strong archaeological piece to some of the work that we did, we started using our 3D laser scanners, an Optech Ilris in this case, traveling around the globe to a few places and recording the built environment from many centuries or millennia ago. And so a couple shots here, we're in Ostia Antica, that's the original port city for Italy, and Machu Picchu, and Tiwanaku in Bolivia. And one of the things that we realized, it's a little hard to see, but in the kind of in the middle there, that's Tiwanaku data, and we actually combined data from aerial photography, airborne LiDAR, terrestrial LiDAR, all these things together into one system. And then something kind of interesting happened for me personally. We had our founding director, Fred Limp, who was actually an archaeologist by training. He was really, kind of a pioneer in GIS. He was actually one of the founding members of the Open Geospatial Consortium. He wrote a series of articles for one of the trade publications called An Impending Massive 3D Mashup back in 2006. It was a 3-part series of articles, and what he was looking at was how we've got the AEC vertical market, we've got the geospatial domain, we've got gaming domain, and everybody's really working on the same problem but from different perspectives. We want to be able to accurately model the world in 3D and be able to attach attributes on it that we can use for various things and be able to share that easily. And we're all working on the same problem from different directions, different standards, different ways of talking about it, but we're heading towards the same goal in the end. And that's kind of where I'm heading with the rest of this presentation. So what I want to talk about for the rest of this presentation is 2 key areas that we work in and think about. First of all, reality capture. I think that's a good term for that. I actually stole that from, oh, darn it, just forgotten his name. He's the acquaintance of mine who's actually, I think he got the title of Director of Reality Capture at Autodesk when Autodesk bought his company, Alice Labs. It had a very nice point cloud engine. And I thought, yeah, that's a good title. And then I want to talk about modeling, analyzing, and managing that data for the built environment. So first of all, actually, since it's such a small audience, let me just get some feedback from you guys. How many of you work with any point cloud data at all right now? Anyone? A little bit? Okay. Laser scanners or photogrammetry? Both?
Laser scanners.
Okay. So first of all, I just want to talk a little bit about the sensors that are out there, just to kind of let you know what we're talking about. Basically, 2 classes. You've got active light source sensors, and you've got passive light sensors. So in active light sensors, we're talking about laser scanners mostly. We have time of flight scanners, which are like the total stations. They're sending out a pulse of light and measuring how long it takes to get back. And these give you the longest range, and in general, probably the lowest noise, or potential for the lowest noise. And several of the major vendors like Rigel, Optech. The scanner that I have in the other room in there is a phase-based scanner where you're superimposing a wave on the light signal, and what you're doing is you're measuring the phase shift of this wave as the light's reflected back to it. It's a constant waveform that's being superimposed on the light beam. It doesn't send out discrete pulses, it just measures it at different times. And so these are fast. There's ones that do at least a million points a second, the measuring. But they do have limitations on the distance, which is tied to the wavelength. They can only measure one wavelength away from the scanner. And so the one I've gotten there, 79 meters is its maximum. There's some out today that easily double that. And if you Go past that distance, what you get is you don't know where the measurement came from. You don't know whether it's one wavelength away or two wavelengths away, and so usually the power and the distance is kind of matched. Our scanners are ZNF. Ferro's a big player in this market. And so those are the kind of the two classes of laser scanners we use for what we call mid to long range use. Then you also see structured light scanners, and these are the Kinect type devices, right? In prime sense, structured light that can be inexpensive because all you're really doing is projecting light and you're using cameras to then capture where these dots are or the bars are on the object that you're measuring. And they usually require relatively low light conditions. They work pretty well indoors, out in full sunlight. Well, you got to project light, so even if it's infrared or something, it's going to be difficult to see. And these structured light scanners can be expensive. We have a very high resolution, $150,000 scanner that we use for scanning artifacts. But most of what we see today are inexpensive ones. In passive light, this is what we call photogrammetry. And so in photogrammetry, all you really need is a camera. The better the optics, the easier it is to work with. Software is relatively inexpensive. There's something from a Russian company that we think is still probably the best one out there called Photoscan. Visual FSM is a free for academic, inexpensive program. 123D Catch is Autodesk's online product. And these are all relatively inexpensive because the sensor is just a camera, and you go out and take lots of pictures, and it seems like an awfully good way to acquire data. There's really multiple steps involved to using one of these sensors. You're going to, first of all, take your pictures, and you've got a very fancy algorithm that didn't exist before, like 95 or so, that does autocorrelation. Basically what it says, I've got two photographs. I don't know what angle they were taken from. I don't know anything about them, but what I'm going to do is I'm going to automatically put in these multidimensional descriptors of points that we think we can match with other photographs at multi-scales. And it can do, these, if you've got multi-megapixel pictures, you can get hundreds of thousands of potential points that can match up, and then the algorithms are going through all of these photos. You don't just need two photos, you can have literally thousands of photos dumped into the software. You press the button and go away for a while, and it will go through and it will automatically autocorrelate all these things, and it will actually calculate the positions for where the camera focal planes were, and that's how you can then build a surface. So the next step of the process is then, once you know the camera positions, where the images were and how they fit together, you can densify your surface. And that's a separate algorithm, and some products do one part better, some do the other part better. But in the end, no matter what kind of photogrammetric solution you use, you need to know either exactly how far away your camera is from the object that you're measuring, or you've got to scale the result, because it can be quite accurate measurements relative to each other, but it doesn't know how far away the images are from your camera. And so you have got to scale it somehow. So that's an issue. That's one of the big issues. The second one is what I'll call here just cumulative error. So when you have all these photographs and you start stitching them together, this is all math, and there's error to this math. And when you start doing it over a large area, it starts adding up. And unless you've got some sort of control, survey control, points spread all around, you can't correct for that. Now, some of the software like Photoscan, you can actually put in control points and actually make it pretty good. The other thing that you don't readily have in most of these programs is you don't have any way of assessing whether or not there's a bad match on the points. So it can give you a bad measurement, and you've really got no way of knowing that. Whereas with a laser scanner, you can look at things like the angle of the reflection and go, that's probably not going to be a very good point to get a measurement off of. In photogrammetry, it kind of is what it is. If you do it well enough, it can be quite good. Otherwise, maybe not so, and you don't really know. And if you're looking at sensors to do this type of work, there's 3 things you've got to know about. And this is, if you're going to be looking at data or purchasing an instrument or using an instrument, you've got to educate a little bit about what these things actually mean. Because there's 3 different ways of measuring how good your result is, and they're not the same. And in some cases, they don't use the same ways of assessing. Well, in almost all cases, they don't use the same ways of assessing these. They kind of favor what is good for their instrument. And so, first of all, accuracy. How good, if I say it's here, how far away am I from that spot? That's your accuracy. Okay, and that's a number you obviously want to know what that what it means. Precision, though. They may say precision, they may say noise. What they're talking about is what's the repeatability of that measurement, right? So if I say it's 10.213 meters to that wall there, and I measure it again, it says 10.315, and then I measure it again, it says 10.1, that's the noise, it's the precision. And so that matters too. And finally, and this is the one that you've got to really ask some serious questions about, is resolution. So we're talking about what can we actually resolve. If I can scan with the blue scanner in the other room, I can scan across the room, I can tell it to go ultra high density. I can make the points at I think it's at 10 meters. I can make them like 1/4 of a millimeter apart. Okay, that sounds wonderful. Does that mean I get 1/4 of a millimeter resolution? No, because the light beam has a finite size, and it's bigger than 1/4 of a millimeter at that distance. And so I need to know that when I'm talking about resolution too, because that matters as well. Because averaging the measurements within the diameter of that light beam. So if you're looking at getting something to use for this, there's something you need to understand in terms of this triangle here. You've got accuracy, you've got speed, you've got cost. Right now, there's nothing that will optimize those three parameters. If you want accurate data for as-built models of a building that you can compare to the original BIM models, if you want high accuracy, you're going to need to be using an expensive laser scanner. You're going to be looking at accuracy and speed. It's not going to be cheap. If you want to simply model a room to visualize it, then we can look at cheap. So, for example, 2 days ago, I just bumped into this morning, actually. So this is on CNET News. We've got Matterport talking about their new $4,500 camera that does really nice, really fast 3D modeling. And it's a great machine if what you want is a not bad model for visualization or figuring out where things go and things like that. But if you're trying to put together an accurate as-built model for an entire building or something, this is not going to be what you want. Okay, it's not. By the time you've spread around the entire building, it's not going to have the kind of accuracy that you need. Okay, I'm going to shift gears a little bit and show you some of the work that we've done. We've got a nice sandbox at the University of Arkansas because we work with the facilities management folks on campus. And so we've done a couple projects with them last year or two. And one thing we did was they were going to put a new boiler in the hot water plant that heats the whole campus. This winter we needed it a lot. And so we went and we scanned their hot water plant here, and they knew the size of the boiler, and what they wanted to do, what they'd done in the past, was they had taken the scan data that another contractor had collected, and they had it modeled, turned into CAD data, into actually 3D data in Revit, and then they were going to look at interference with it. And so when we went in there, we said, okay, let's just see how good a model we can do without even converting it from a point cloud. And so we went in there and we did quite a few scans and high resolution. And so after they started looking at the data, they said, you know what? We don't need to convert this to CAD or BIM because we can take every measurement we need directly off the point cloud. And that actually saved a whole lot of money because right now, the problem is, how do you get this point cloud turned into 3D models, what we call CAD primitives, that can then be used in, in a BIM that we can then attribute. And that's a difficult problem right now. We can actually see in this drawing, let's see if I can wave my mouse, no, it doesn't work, okay. That lower left drawing there, you see some kind of gray pipes there. Those are actually models. Those are actually extracted by some of the software, just showing some of the piping. And so those can be pulled out directly into Revit. Or, I bet the guy's not here, so I don't have to say Bentley. And anyway, some objects are pretty easy to extract right now. Things like pipes, cylindrical objects are fairly easy to automate the extraction because the surface is extremely regular, easy to predict. Walls are pretty easy to predict, except we got lots of, over here we've got two planes. We've got a Facebook poster that sticks out 2 inches. We've got all kinds of lumps and bumps on the wall. How do we decide what's a wall, what's not a wall? Over there, I've got some kind of a board sitting in front of a curtain. Is that a wall, or is that just, how do we decide that sort of thing? And so that's much more difficult to automate. And then we start worrying about how do we automate extraction of things like tables and chairs and things that are inside of rooms. That becomes even more difficult. And so right now, that operation is largely done manually. Okay, there's some software that can automate processes of it. It's neither cheap nor is it 100%, but it definitely helps save them some time if that's what you do for a living. And it's going to get better. So this is the same data right here, and I'm going to show you, if I have time, I will show you this a little bit later. Actually, what time did we finish? Greg, do you know?
Actually, I don't know.
Okay. All right. I'll keep my active for a bit. I've got some data loaded where I can show you one way of easily taking measurements off of some of this data without having to have a expensive point cloud software. I'll show you one of the solutions, but basically we can put data up on the web and somebody can go in there and take measurements based upon this point cloud quite accurately. So then I wanted to show you another more interesting project. So we have a building on campus which was the original library for the school, and it's been used by the School of Architecture for, I don't know, probably the last 50 years or so. And recently they decided to completely renovate the building. They tore out the old stacks from the library that weren't being used anymore, and they added offices and higher quality space, and they remodeled the entire building. And so we were asked to come in and do two things. We were asked to come in and take scans pre-demolition to preserve what is a historic building. And then we were asked to come back and basically scan the post-construction building so they could look at that. But as we went along, we started talking to some contractors and showing them some of the data, and they said, could you scan this, and what could we see if you did that? And so we did the pre-demolition work, getting the interior and exterior of the building, as well as using photography and photogrammetry. Remember, I was kind of dissing photogrammetry? Well, photogrammetry is good if you're not trying to model an entire building. So if you've got architectural detail, rather than taking several different scans in there, tying up a $100,000 instrument, I can send someone over with a camera that knows what they're doing, take a bunch of pictures, and we can tie that into the rest of the data. And but then we also started scanning in every construction phase. Every time that they installed new systems, mechanical engineering, electrical, plumbing, we would be in there taking a scan before they put up the sheetrock, before they put down the raised floor, before they put up the ceiling. And so we've got all their systems scanned in before they were enclosed. Furthermore, as the contractors saw this, they were getting ready to pour a large area that had post-tension cables. And they said, right now, if we have to come back and make a cut in this floor a few years from now, they're going to have to hire someone with ground penetrating radar and figure out where the cables are so we don't cut through them. And we said, that's not very clever, is it? And they said, could you scan this and could we measure? We said, sure, why not? And so that's what we did. At that point in time, we had a wonderful vantage point because they hadn't finished closing off that part of the building. And so we actually scanned from a roof adjacent to it. And we showed them sample measurements so they could go and compare. And they said, yeah, that's spot on. And so lastly, we finished the scanning of the entire building. And so now we have before and after shots of the entire building. And so now actually, I'll just come back to this, getting ahead of myself here. This is the, in the lower left, that's the building before the demolition was finished. This is this is the main area, is the architecture, I can't think what they call it, it's their lab, is where they go and do all their drawings. This is before the demolition. This here is during the demolition, so all pictures taken from the point cloud. And over on the, over here, this is down one of the rooms downstairs, and you can kind of see a little bit in the upper left-hand corner. There's actually some modeled ductwork in there. And so then below, what we've done is we've combined that scan just as a 2D shot with the floor plans from the original floor plans from the building. And so they can go in there and take measurements off the original floor plan and see what they've got. But what we are proposing now to the Department of Energy, we just sent in a pre-proposal with a colleague of ours who's moved away to the University of Maryland, and he works with very low power and environmentally powered sensors that measure airflow, temperature, pressure differential. And so what we're looking at doing is taking an Asbuilt structure that's been remodeled. We're planning on using the same building that we've been showing you. We have very accurate scan data. We are going to model it into Revit or similar environment, and we are going to then sensor the building, and we're going to be using, this is one of the, in Arkansas, it's one of the first remodeled LEED certified buildings. And so we're going to see, does it really meet the specifications? Things change based upon the use of the building and the users of the building. So we want to be able to monitor that and see what can be done to optimize it. And so we think there's a lot of potential going on there. So finally, switching over to the modeling, analysis, and management of this data. From where I stand, it's not about building information modeling, it's about building information modeling, analysis, and management. And so I grabbed this little chart here, which is from our friends up at the Computer Integrated Construction program up at Penn State. And they had a team looking at BIM planning, put this together, that these are 25 different categories of uses for BIM data. And the dark blue ones are the primary categories, the light blue ones are secondary categories. And so if I look at these here, I look at planning, and I see, we've got analysis and looking at existing condition modelings. From my perspective, you should be using geospatial data if you're going to be doing that. Under design, we've got a couple types of analysis that are going to use existing site data. Under construction, we've got site utilization planning. Again, we want to know, what's the terrain, we want to know the soil types, all that stuff. And then operational, we're looking at disaster planning, we're looking at space management and tracking. These are all spatial problems, and in most cases, we've got some geospatial needs there too. So from my perspective, we should be using geospatial coordinates. Unless you're making 50 of a building and you don't care where it gets dropped on the ground, we should be working in geospatial coordinates from the beginning. And we should make this data where it can be easily improved in detail, shared with others. And here, let's take a look at this. And I realize other people have studied this, but I just kind of seated my pants and said, okay, let's say I've got an institutional building, and I'm going to have 4 years to plan, design, and construct this building, and I've got a 50-year life expectancy. 93% of that life cycle is in operation, right? And so that's what we really should be thinking about with, where does this data go? Who's going to get the most out of it in the long run?
Malcolm.
Yes.
Question: why do you suspect it's not more frequently used within the building industry?
Well, I think it's partly legacy. It's where you're coming from, and do you see an immediate need? And so we know that that landscape architects are using geospatial data, a lot, but they're not necessarily doing the detailed models. So then we go to the architects, and the architects are doing, 3D CAD, but then somebody wants blueprints or 2D drawings, and so we're losing our 3D data again, and perhaps we're worried about, you know, a suitable projected coordinate system for the location, perhaps not. And then, you know, post-construction, does the architect, unless somebody's saying that you've got to do this, this is part of the contract, you know, why do I want to worry about the operations of the building? I don't think it's, well, Greg, I mean, you can talk all about this and
No, it's
Yeah.
good to have the geospatial perspective.
Yeah, I think, well, there was actually, this right here, this is Dale Lutz again he's the VP for Safe Software, and he went to a session at Autodesk University back in 2011 that one of the sessions they had there was his favorite, was the Great BIM versus GIS debate. And one of the attendees' comments that I thought was really interesting, this architect said, it's not really an information model, it's an information model about a building rather than a building model with information, right? So it's really in the long range view of a building, it's really about the information, even more than the model of the building, right? It's really about all the attributes that go with it. And right now, I mean, you know, the CAD and 3D BIM type software that we use, we can do more and more attribution, but most of it's still oriented towards construction fabrication sort of things and not the operating side of the picture. And I would like to see everybody talk better together. We don't have to all write the same software. We don't have the same audience that we got to share. But in the end, we need to be able to move data back and forth, generalize some of it, make some of it more detailed, without having to go to a lot of work. So what we need are some standards, and these are coming slowly. But if I look back at GIS, especially 2D GIS, you know, we started developing open standards, I should say, you know, back in the early 90s. And today, there's all kinds of wonderful tools out there that we use. You know, we're all on our devices here. We all got all these great location-based tools that we use all the time, and we don't think about, you know, where this first got developed from, because now all the tools are there when anyone can go and use them easily, and they don't have to be a geographer to use them because all the information is there, the standards are there, all they got to do is plug it into software that they need. And I'd like to think that in another, you know, 5 years maybe, that we see the same thing happen, you know, fleshed out. I realize this started right now, but to get it where all the players in the AEC software industry can start to, you know, move data back and forth between different use cases. I wanted to show up this too. This is the AIA AGC level of development chart here. And these descriptions seem pretty good to me, actually. But when I get down to the bottom one here, it says the model element is a field verified representation in terms of size, shape, location, quantity, and orientation. And I look at that and I go, well, what about my digital fabrication friends? They're going to tell me that this isn't good enough because it doesn't say it's got to be solid modeled or I can't manufacture it. And so we need to be, you know, when we come up with standards, we need to look beyond our little segment of that and say where, you know, who else may be trying to use this, where does it need to go? Back at the university, I just want to show you one last little piece. We've been working with the campus doing these in-depth room use surveys. Who's using these different rooms across campus for different things? And we're getting to the point where on the CAD and GIS side, we're starting to put together floor level maps showing who's using these rooms for what, okay? And it's not difficult to take these and to turn it into a 3D visualization where we can look across this campus and we can say, okay, so where are the rooms being used by this department? No, they're here, here, here. Boy, that's not smart. Like, look, if I'm taking these classes, I've got to go from here and here all the way here. So we can start to not just look at kind of the traditional ways of using some of this data for operations, things like asset management and maintenance. We might want to also start looking at things like social movement analysis, disaster egress plans, and things like that. So this data has many, many more legs than what's currently being used for. We've just got to make it where we can all share it and play with it well together. One last comment, back at that Autodesk University that Bill Lutz went to, someone made the comment about GIS, that stands for Get It Surveyed, okay? And that's what the surveyors used to say about, GIS data wasn't accurate enough. Well, that was the old days. And today, you can get open source software that actually does spatial analysis of circular components, which was one of the things they didn't like about GIS because you couldn't have true circles. There's free software that does that stuff now, good software. And so we're moving beyond that, and we really need to start looking for common ground and seeing what we can build with that. That's what I've got. And I do have here, let's see, there we go. I wanted you all to see, this is actually the room we were in yesterday. So if you want to take just a quick look and see what this data looks like, this is 2 scans taken opposite ends of the room. The actual 3D data took about 3.3 minutes to collect on each end. And if I zoom into my clock right here, just so you can see what it really looks like.
Pretty cool.
How do you build that in 3 minutes?
I press the button.
Wait, how did you collect it?
3D laser scanner. 3D laser scanner. Yep, it's in the back of the room in there. The blue thing on the tripod. And so I measured some of these are about I think it's about 3 millimeters between the points on this clock here. Maybe even denser than that after looking at it. So lots and lots of data. If anybody wants to access some of this data for using in the hackathon, I've exported it as an ASCII format. Here's the gotcha. Right now, for the entire room, which has the ceiling on it too, I've cut that off. It's about 3 gigabyte. 72 million points, XYZ, intensity, RGB. So if any of you would be interested in taking a look at any of that, I've got it ready to go. So,
Excuse me.
yes.
I'm not sure, I hear you, but I'm not sure how from this you can help the life cycle building, like how to connect.
Well, this is Asbuilt data. And so, I mean, we all know that what's planned is not what gets built, right? And so this is a way of assessing what's there now, of accurately measuring what's there now, especially if it's a building that's not it's not new construction. I'm coming back in and trying to make my building more efficient, remodel. Here's a way of very accurately measuring what's there. Okay, and if you want to measure change, if you ever have to worry about movement of a building or something, we can measure it very quickly here too. But it's getting to the point that this type of data is becoming very fast and pretty inexpensive to collect. You can get a very good scanner now that does survey type measurements for just a little over $40,000. Sounds like a lot of money, but not really, right? And these things last a long time. We're using instrument that's from 2003. That's much slower. It still works. And I mean, there are so many use cases for the data. The problem here is, do we need to take what's in points right now, or do we need to move it to something else? In some software, we can represent these points as voxels, right, volumetric pixels, and we can do certain types of analysis without having to convert it to anything. And so this is one of the questions: is do we need to convert it? If so, what's the best way to do it? This is a big data question too, because we've got sensors today that can go and collect all kinds of data, but the output is large. If I spend half the day scanning with my unit in there, I've got 30, 40, 50 gigabyte of data from half a day, and it gets big quickly. I did want to show just one other quick image here. This is a way of looking at data. This is one company's solution. I do not, basically, I do not declare that this is the best. This just happens to be what we have as part of the Leica package. And so this is the same 3D scan data with the color mapped to it, but through this web plugin here, I can only view from the actual scanner location. I can't put together multiple scans, but I can measure everything I can see from this scanning location. I can measure just as accurately as I can in the real point cloud. So if I want to know, what's the total width of this rack of pipes, I can click on, I can say measure here and say, click on point here, see where we're going to go from there, go to there, and oops, oh, I used the wrong tool. Anyway, sorry, that's 1.4467 meters. It's hard to read there. But, I meant to use the measure tool, which is this one. It's a little different. There to, so here's my measurement right here. And so what's nice about something like this is that you can give this to your operations people, you can give this to your maintenance people, saying we're going to be cutting behind the wall. All this is being covered up. I want to know how far away from the wall is my conduits right here. And so I can go and measure it without having to take off the sheetrock or pull up the floor or whatever. And this can stay in existence as long as the rest of the building does, right? And so it's just a matter of ways, it's how do we best use this data? This is right now the best as-built data that you can get. And it's getting cheaper and cheaper all the time. How many of you have seen Project Tango? Okay, so basically Google's about to deliver 200 phones with depth map cameras built into them for development use, and so I can actually map out a room from my phone. It's not going to be as accurate as that, but hey, it's all coming, right?